All right. Welcome, everybody. My name is Luke Pinkerton. I am the founder and CEO of Helix Steel, and I am also a structural engineer. Been working in the field of concrete construction for just about 20 years at this point. And I am very excited to share this topic with you today because it's something that I definitely get excited about. It's something that I think is needed in our industry to address many of the challenges that we're faced with, as well as sort of a growing appetite to create more creative forms in our building construction. I've always been interested in architecture. I've never really had enough of the creative mindset to be an architect, but I've always kind of followed it. Being an engineer. This is a structure that it's Santiago's Calatrava. It's in the Canary Islands. One of the reasons I'm just fascinated by it is both from the form that you see there, but also structurally. I'm thinking, how do you deal with the stresses in this shell-like structure with the construction methods that we have today? It's very challenging, and I think that this is certainly not the default type of structure, because to do it can be done. It's just very costly, as opposed to more of a boxy structure that we typically see. I mean, a lot of the major construction in the United States right now, or the last couple of years, has been in, I think, areas like warehouse construction, hotels. We're just doing sort of orthogonal structures, and that's because it's cheapest and easiest to deal with the limitations of the materials we have today. So I think in the future, we're going to be looking to do things that are more interesting because they're more appealing and perhaps more functional. But then we also need to be doing them in a more efficient and sustainable manner. So one of the things we're going to, we'll cover this a little bit as we go into the presentation. But one of the things, if you've been in any of my webinars or presentations, that I'd like to kind of refer back to is the Portland Cement Association's roadmap for carbon neutrality. And in that roadmap, you can download it. I don't have a link here for you, but you can just Google it. It has a challenge for our industry in terms of how do we get better in terms of our construction technology. And today we're going to cover a couple of the areas that are outlined there. And I think, this applies not just to creating more sustainable or carbon neutral structures. It applies to just creating better structures and more efficient structures as well. So, this is what the Portland Cement Association said we needed to do as a construction industry to achieve that carbon neutrality target by 2050. In addition to, there were some other areas that they identified outside of the construction in terms of designing and building. What we're going to focus on today is optimizing concrete, and then we're going to talk about construction technologies as well. There's a whole nother area of over-design that I had originally intended in including in this presentation, but as I put it together, it became too much. So we're going to save that for a future webinar. And then obviously education, and that's kind of what we're doing here today. This session is not, certainly we'll cover some things about our Helix product through this, but it's really about trying to start to think about what's next in our industry. So just a little bit about how this works. I have Peter, who works in our construction or in our project management, sales project management group on. It looks like he sent a couple of texts here. If you guys have any questions or want to get any additional information along the way, go ahead and just type your question right into the chat box. I may try to get some audience participation as we get through here, just to kind of keep it active and engaging. So there'll be a couple of times where I ask for some feedback, but you can see that chat box that's in the right-hand side of your window. I'll also be providing some links and QR codes for you to use to research some of the things that we talk about today. So as I mentioned before, we're going to really talk about material optimization and construction methods today in terms of innovations. So let's dive right into this. So one of the things that's kind of interesting is we are kind of working with materials that kind of have some fundamental limitations, but in order to really understand those limitations, we need to just kind of go all the way back to solid mechanics and talk about some fundamentals of materials and define those fundamentals before we get into the details. So, very basically, there's in any structure, you've got tension and you've got compression. Those are the fundamental forces that you see inside solids in particular. Shear is a form of tension at an angle. So it's at a diagonal angle typically. Bending is actually a combination of tension on the bottom face of a member and compression on the top face of a member. The material that we use and the material that we're going to focus on today for construction is obviously concrete. Concrete is fundamentally an amorphous material. It's a mixture of different materials that are glued together, essentially. Fundamentally, it is pretty good in compression in terms of its strength, but not as good in tension. It actually, the tensile strength of it's only about 10% of the compressive strength of it, which forces us to do some things from a design perspective that are somewhat limiting. The other issue with concrete is that it's fundamentally brittle. And we're going to talk a little bit about types of materials. I apologize, the resolution on this stress strain curve. This is a tensile stress strain curve. And we're going to really be talking about a couple of different types of behavior. So pretty much any material will have some amount of behavior that's considered elastic. So elastic means that it acts kind of like a spring. So if you load it up to a certain point and then you unload it, that spring or that concrete will return to its original form. Once you reach what we call a yield point, there'll be some damage or some change to the material such that if you unload it, it doesn't come back to its original shape. So plain concrete is elastic up to the point of yield, and then it's completely, it's brittle, which means it just completely loses its strength once it cracks. There might be some period here of some micro cracking that occurs, but unless there's some reinforcement in there, it's going to snap and it has no additional strength. So that's a brittle material. The other material types we're going to talk about is what's called strain hardening. And when we talk about strain, we're talking about direct tension. So strain hardening materials actually get stronger as the strain increases. So you get a yield point, and then the structure of the material changes and it actually hardens. You see a little bit of hardening actually with steel. Steel actually has a hardening just before it actually fails after the yield point. There is a technical class of material that doesn't harden or soften. Sometimes that's called perfectly plastic. That's usually just a modeling assumption. The American Concrete Institute, for instance, models steel as an elastic, perfectly plastic material in its design codes. And then there's something called strain softening, and strain softening materials actually get weaker after they reach that yield point, but they don't completely lose all their strength. This class of material is a little bit more difficult to use because typically when a structure is loaded up, the load doesn't go away. So if you have a load that loads the structure up to a stress up here, that load doesn't go away. And if that load remains at the same level in a strain softening material, in essence, that strain softening material is going to behave in a brittle manner, just like plain concrete. It does have some applications where there's the load is more of, say, an enforced displacement, where having some, what the industry sometimes calls residual strength, has some benefit. So there are many different ways that we have tried to improve the properties of concrete, but fundamentally concrete's been around for a long time. This is sort of what the microstructure of ordinary concrete looks like. Obviously, reinforcing bar, or this is like a bar mesh, deformed bar mesh, different types of fibers, our product, which is called Helix Micro Rebar, and this is actually the microstructure of something called ultra high performance concrete. So this is just a little primer on solid mechanics before we jump into things here. So being in Detroit area, we are in Ann Arbor, we hear a lot around here about autonomous vehicles. Some of you may have a car that has some autonomous vehicle features. I know myself, I have a Ford that has an adaptive cruise control, for example, which could be considered maybe a level 1 or level 2 automation type system. If you happen to be the owner of a Tesla, you could probably argue that your car is automated at a higher level. But basically, the American Society of Automotive Engineers, SAE, has come up with a forward-looking scale or level system that identifies just how autonomous a vehicle is. And certainly the automotive industry has its faults, but the rate of technology advancement certainly is I think we can safely argue has happened faster than the rate of advancement in concrete or reinforced concrete design, given that concrete's been around for probably 6,500 years and is fundamentally similar to what it was back then. And reinforced concrete's been around for 200 years. And, sure, there have been refinements, but we're not, moving quite as fast as the automotive industry that's only been around for probably around 100 years. So really what we're trying to do is get to this level 5 automation, which is basically, you don't have to do anything. You get in the car, you tell the car probably verbally where you want to go. It'll take you there, even if it has to go over a dirt road. Even if it has to go in a country where there's no access to, internet, for example, it doesn't require any intervention at all. That level of automation is a ways off. I think they're finding that it's very challenging to do because of the computing power. You have to have basically artificial intelligence type technology to be able to do that safely and reliably. But some of the features like that adaptive cruise control I have in my car are quite nice when you're on a long trip, and takes a little bit of the edge off of driving. So given that I have friends that are in this industry and I hear about it a lot, I kind of started to think about, how might this type of approach apply to what we do in the concrete industry? Obviously, we're not building cars, but what if we were to think about materials, construction materials, in terms of a level system, and more specifically, concrete materials? Whereas you start with level 0, which is similar to like a car that's probably from the 1960s that didn't even have cruise control. to a level 5, which is something that we can't even possibly imagine at this point. Maybe we can imagine it, but we don't really think it's even feasible to apply from a construction perspective. So what we're going to do is walk through this proposed level system of concrete materials and talk a little bit about where the state of the art is, and what the advantages of progressing down this level system might be from an economic and other sustainability, other factors. So if we start at level 0, which is just plain concrete, actually plain concrete is quite impressive on its own, but it requires quite a bit of compromise in terms of the design. We certainly can't do anything like the structure that I opened up, the Canary Island Auditorium, with plain concrete. However, 2,000 years ago, there were engineers designing dome structures like this with optimized concrete materials that actually incorporated lightweight concrete as well as heavier duty, higher strength concrete in a structure like the Pantheon here, that has really stood the test of time. And the reason it stood the test of time is this structure is designed really to be inherently stable. It's completely in compression. So if we remember the solid mechanics discussion, concrete's very strong in compression. So what the engineers, back in Roman times did is they knew that, they understood that. If you look at a projection of this dome, it is a perfect circular projection. They further made it more robust by lightening the material here. There's no rebar in it to corrode and deteriorate over time. Certainly, they've made much larger domes since then. One example is the Seattle King Dome. That's about 10 times the diameter of this. This one, I think, is about 142 feet in diameter. So the King Dome was like 1,400 feet in diameter. That structure only lasted about 25 years. And part of the reason they took it down, other than sort of the mixed-use stadium concept kind of dying with the 80s, was that they had a partial roof collapse or a partial ceiling collapse that was caused by corrosion. So using rebar and putting structures up where the concrete is not really functioning, we're relying on the rebar, makes it more unstable as a structural design approach than plain concrete. The other interesting thing about concrete is it's been really around. They have evidence that it was in use around 8,500 years ago. Obviously, the form that we use now, Portland cement, has only been around for a couple hundred years. But fundamentally, the way that it was done with other, the polyzonic materials prior to that, is quite interesting if you research it. So that's level 0, or level 0 is ordinary plain concrete. The American Concrete Institute has definitions for this. Normal strength concrete is defined in Chapter 19 of ACI 318. Typically, it involves concrete that's around 2,500 to 5,000 psi compressive strength. If you go and look at ACI 224, there are tables that show approximately what the ratio of that compressive strength is. If I go to, say, 2,000 or 3,000 psi, you'll see that the tensile strength of the concrete's about 9%. I called it 10% earlier. So we're talking about tensile strengths that are, for a 4,000 psi mix, probably around 400 psi direct tension. Now, I'm going to be flipping back and forth between flexural tension and direct tension a little bit here. Flexural tension, or modulus of rupture, is a little bit different. It's not exactly the same. Direct tension is actually a little bit lower than modulus of rupture. Modulus of rupture is another form of measuring tension, but it's looking at it in a bending format. So Just remember there's a little bit of difference there. We won't get too much into the details of that, but we'll be kind of talking about them in a similar light. Modulus or rupture is typically a little bit easier to measure with concrete. So that's our level 0, which is basically plain concrete, which is brittle. Our compressive strength's about 10% of, or our tensile strength's about 10% of the compressive strength. We call this pre-crack. Really, this is the point at which it cracks, is about 10% of the compressive strength. And then after the concrete cracks, it has no tensile strength whatsoever. So again, going back to this, we're going up this elastic curve, we're snapping and then just coming straight down. So the next development, and again, this has been around for a long time as well, and it can be accomplished by doing things as simple as reducing the water cement ratio in concrete, and that is high strength concrete. So by reducing the water cement ratio, keeping the concrete level or the water level low, which can be done without adding more cement with some of the modern shrinkage reduce, or not shrinkage reduce, super plasticizers and water reducing, high range water reducing admixtures, et cetera, you can get higher strength concrete. And ACI defines high strength concrete, I think, at 6,000 PSI or higher. Certainly, it can be done by just adding more cement. Given all the pressure right now on creating lower carbon impact, that's not necessarily a great way to approach it. But like I said, you can reduce that water cement ratio quite easily by using a water reducing admixture. As a result, we can typically get quite a bit higher than that 400 to 500 PSI tensile strength that I mentioned before. One of the things that you can do with this, certainly it's often used in high-rise construction in areas where high compressive strength is needed. However, the American Concrete Institute does, in Chapter 14, allow for design and use of plain structural concrete. And the allowance is based on the compressive strength, or the square root of the compressive strength. So if I have, say, a 10,000 PSI concrete, I can get about twice the usable structural capacity in that 10,000 PSI concrete versus a 5,000 PSI. Well, it's not, it's a function of the square root of that ratio. You can get more. It's not a 1-to-1 ratio. You can get more, which means you can use plain concrete for more applications than is possible with just ordinary strength concrete. Some of the drawbacks of high strength concrete are that sometimes the shrinkage can be higher because you have more cement, and cement is the component that shrinks in the mix. But that doesn't mean that you can't engineer around that. So going back to our scale, if we go to high strength concrete, we can definitely get more out of that concrete. We get more than that 10% of 500 PSI or so. However, it's still brittle, and that's a limitation. The positive is that with higher strength concrete, we can design structures that are structurally load bearing under ACI 318, Chapter 14, which is the plain concrete section. You can do walls, footings, and structural slabs on ground that are thinner than with normal strength concrete. And then also in slabs on grade and pavements, because that flexure or that compressive strength or flexural strength in the case of pavement design is a primary factor of design, you can typically thin up those structures theoretically the higher the strength of the concrete gets. However, you really haven't these are just incremental changes because fundamentally the material is still brittle. Once it reaches its peak, it just snaps. So the next development we'll talk about is fiber reinforced concrete. Fiber reinforced concrete has been also around for quite a long time. You can certainly, depending on how well your Google searching skills are, you can find accounts of it being used thousands of years ago. You know, you always hear about people using horsehair and things like that, hay, straw, in even Roman times to reinforce their concrete. But the modern fibers really probably came about in the early part of the 1900s in the form of slit sheet metal or melt extract from steel processes. The technologies have been refined over time. First with steel by adding deformations along the length of the steel or end deformations like these hooks. And then more recently with the development of various plastic or synthetic fibers that are out there made of these types of polymers. The fundamental difference between steel and polymer is really its stiffness and its weight. So obviously the polymers are about 8 times lighter than the steel. Obviously they're not made of steel, so they don't corrode, but they're about 10 times softer than the concrete itself. So the concrete doesn't tend to react to it until cracks have formed that are large enough that the fibers can start to stretch. And I'll show that in a minute. Steel, however, is about 10 times stiffer than the concrete, which means that if its bond is good enough, it can actually have an effect on the initial cracking or the modulus of rupture of the concrete. Not the concrete itself, but it can basically hold the concrete in a micro cracking load redistribution phase such that it can carry, there's a small region of hardening after the initial micro cracks form. So these are some of what the products look like. That's a point about this is the modulus of elasticity, which is the stiffness of these materials. So we're involved, or we have been involved with the Minnesota Department of Transportation's research initiative, the NRRA. They recently did a pretty comprehensive study on a variety of fibers, not including helix, but including just traditional like hook-ended fibers and different synthetic fibers. And they characterized the behavior of these products under compression and bending and tension in a bunch of different ways. And you kind of see the benefit or maybe the limitations at the same time with these products. Really, these products, what you're going to find is they're going to provide some degree of softening benefit, but they're not really going to have any effect. Actually, they actually have a little bit of a negative effect. This is effectively dosage on this scale and compressive strength. The more of these products you put into the concrete, the more there's a point certainly at which because they demand paste on their surface, they start to negatively impact the properties of the concrete. So, a lot of these products are on the steel side are applied at dosages like 60 pounds per yard and above. On the synthetic fiber side, 3 to 7 pounds. And the problem with applying these high dosages is that that it affects the wet properties of the concrete. It demands the paste and it actually can weaken the concrete. You can see that. It actually can reduce the compressive strength of the concrete. Now, it's not that significant, but there is some effect. Now, these issues can be dealt with by altering the mix design, but in this case, the mix was kept exactly the same. Same thing with modulus of rupture, which is a measure of the tensile strength. We actually get a slight decrease, especially with the synthetic products. And part of the reason is because of the mix design issue I mentioned before, but also part of the reason you can see a little bit of increase with steel because it is stiffer than the concrete. But the synthetics really don't, the concrete doesn't see the synthetics until after it cracks because it's softer than the concrete. So this is some specific examples of what we call residual strength measurement. And if you remember the solid mechanics lesson at the beginning, softening is a case where the stress goes up to a point and then it goes down, but it doesn't go completely to zero. So if you run a test, this is called ASTM C1609. It's a test that's a little bit controversial in the industry because it doesn't measure tension directly, number one. Number two, it's a machine, the curve is generated by a machine that really controls the displacement, not the load. So again, if you had a constantly increasing load, this would just go straight to zero. But because this machine very carefully loads this thing up such that this crosshead moves at a constant displacement rate, inches per minute down, it can actually measure what happens after a crack forms in a softening material. So if you take a synthetic material, this one kind of looks like a yarn type material. Those of you who are in the industry might know what product this is. I'm not going to name names, but you'll get a curve that really doesn't have, there's not really any effect on this peak as we saw in the last plot. This is the load that's being pushed down, and this is the displacement at the center. You'll almost come down to zero load. And then what happens is these pieces, they fray out and they engage the concrete and they start to stretch. And as they stretch, you get a nice residual strength that's either constant or it can even be increasing. It's like a rubber band stretching. And what you'll find is a lot of the folks that market these really like to talk about their behavior out here because that's where it's best. In terms of whether that's best or not, if you're just concerned about kind of what happens at an ultimate condition, that's great. But if you're concerned about serviceability, like for example, crack resistance in a slab, you really want to be more interested out what happens over here where the cracks are still relatively small. These products don't do a whole lot in that area. If you go to a hook-ended product, which has really been kind of the mainstay, I would say, of the steel fiber industry for probably the longest time, you get better performance at that smaller crack width or displacement out here. But what you get is you get a little bit of decrease over the length as the fibers start to, they're not stretching like the plastic, they're starting to pull out. And as they pull out, the resistance that they can provide goes down because really what's governing their behavior is the friction between the concrete and the fiber. So the more of the fiber that's embedded in the concrete, the higher this load is going to be. The end deformations certainly help. Continuous deformations tend to increase the early part of this curve as well. So just summarizing fiber reinforced concrete, what we have with fiber reinforced concrete is a material that does not really affect the pre-crack tensile strength. If anything, it might decrease it a little bit. But it does provide some what we call post-crack residual strength. In dosages that are typically common in the industry and economical, it doesn't provide much. I just put more than zero. Typically what a standard dosage of these products that you might see on a spec, a 3 pound per cubic yard spec for synthetic fibers is going to maybe provide 10% of the peak strength in tension. So basically 1/100th of the compressive strength. The steel fibers, same thing, although you can definitely get higher, and they tend to be a little bit better in terms of keeping those cracks small and serviceable because they're stiffer, particularly if they have good bond to the concrete. So again, this isn't exactly, certainly there have been incremental innovations in different fiber geometries and technologies, but these have been around for a while. So this is a Helix presentation, so I will cover Helix, and I'm going to use Helix as an example of what I defined as a level 3 innovation. And a level 3 innovation is basically going to increase the amount of force it takes to initially crack the concrete, but also have post-crack strength. So fibers in general, as we saw from the MnDOT testing, don't really do the first part, they do the second part. So what Helix does is it does both of those parts. And the reason that it can do that is because it's designed like a screw. It has continuous deformation along its length, which engages it to the concrete without or prior to the development of large cracks that are necessary for that stretching of a fiber. And then from certainly prevents the slippage as well. So again, this is sort of the standard video that I kind of show. After the concrete cracks, we do get this untwisting mechanism, which gives us really nice residual strength. So the product itself, for those of you who are not aware, is 25 millimeters long or 1 inch long. It's made of very high tensile, very stiff steel, and it's twisted. It's rectangular and it's twisted. That twist engages like a screw. It's able to pick up load prior to the development of a dominant crack, which helps us boost that modulus of rupture. Now, it's not going to double or triple it, but it can have a double-digit percentage increase on the concrete. And it's relatively small. Being only an inch, there's 11,500 parts per pound, and it's quite, creates quite a network throughout the concrete that allows us to create consistent behavior. The other thing is the dosage of this, because of its efficiency that we apply, never really exceeds 60 pounds per yard. On average, it's more like 13 to 20 pounds, as low as 4 pounds. And remember how we discussed earlier, if you put too much of a fiber into concrete, it can actually negatively affect the concrete because of the paste demand. We don't run into that issue. It also can be very difficult to finish. So let's look a little bit at the data that's behind those statements. This is some testing that was done by Element Labs as well as Amabel in 2017. You can see the modulus of rupture increase with Helix. You can see we can get into that double-digit increase at a 22.5 pound per cubic yard dosage. This is typically what we would apply in a heavy-duty slab that uses the yield line design method. The 9 pounds is typically what we'd apply to replace temperature shrinkage steel in say, a slab, or to design a wall elastically. You can see over here that as we increase the dosage or the volume fraction, we get further increases in modulus of rupture that are quite significant. In comparison, the orange dots are the synthetic fibers. You can actually see some decrease, and the steel fibers are kind of mixed. You can tend to get a little bit of increase with steel fibers as the dosage gets considerably high, provided you've adjusted the mix to not suffer from the paste starving effect. We measure behavior of twisted steel micro rebar, and we do call this twisted steel micro rebar because it has that additional feature of adding that tensile strength beyond the fibers. We measure the post-crack strength using a direct tension specimen, not a beam test like the ASTM C1609. This is the fundamental behavior that we see in this. We have a peak, we do have softening, but then we have a stable plateau of post-crack resistance that occurs in the region where we're seeing that untwisting that I showed in that initial video. Prior to this, what we call pull-out phase, where the ends of those fibers or the ends of the helix are just starting to pull out. This is what an actual data set looks like out to about 1 millimeter. We have very stable behavior up to about 1 millimeter, and that pull-out region typically begins at about 1 millimeter. So we try to keep our designs in this region in terms of the way that we approach design. And I'm not going to be covering design today. I will provide a little bit of detail in a minute that can give you some more details on that. So just to summarize, for level 3, we're calling it enhanced tensile behavior. We have post-crack strength, and we have more than that 10% of F prime C. We're not really getting there for various, we're not really getting one or the other for these other technologies that are out there, but we do get both for Helix. And the cool thing about Helix is we do have a design approach, an ICC ES ER270 or ICC ES 3949, which covers design using plain concrete methods, where we take into account this, the pre-crack, that provides code approval for design. And then for post-crack, we have the IAPMO ER279 report that allows us to design using post-crack approaches in a manner that has been proven in the market and is cost effective. The next level would be level 4, and the example I'm going to use to talk about level 4 is ultra high performance concrete. Now, I will admit that I was not, certainly I was excited. I was at the University of Michigan when some of the initial work was being done on UHPC back in the 1990s. I wasn't a big believer because I watched them mix this stuff in Hobart kitchen mixers in the laboratory. I watched them put excess of 200 pounds per cubic yard of very fine steel fibers into it. And I said to myself, wow, unless you're going to take a Hobart mixer out onto a bridge deck and you're willing to pay for 200 pounds per cubic yard of steel, which I knew even at that time was quite expensive, much more expensive than the concrete itself, that it would never fly. However, I was surprised by that. The DOTs have found some niche applications for this material, like these connections between beams on bridges, where it actually does make some sense. However, because of its high cost and challenges with implementation, you can't really, it's very difficult to do this. I guess theoretically you can do it in a ready-mix truck, but it's just not really, it's very difficult to do in a ready-mix truck. So it involves using all kinds of different things, reactive powders, high water cement ratios. Typically, the strengths are in excess of 20,000 PSI compressive strength. But with the right combination of concrete mix design and fiber content, you can get hardening. This is strain hardening right here. So you're actually getting hardening similar to what you would see with steel, which is pretty cool. So if they could find a way to better utilize the materials or find fibers that are less expensive, we definitely would be able to. We've definitely demonstrated the feasibility of being able to increase or provide this strain hardening type behavior. The unique thing about strain hardening is now we can start to count on this in, say, a suspended beam application, because we don't get a sudden failure at the point of an initial crack. Whereas with all the levels before, we really need to limit it to applications that fall within ACI 318's definitions for plain or limitations for plain concrete, soil supported members, compression elements, or beams that are, or walls that are laterally supported. Because of that, fundamentally, even a softening material is brittle when it sees a load. So that's the advantage of this. Typically, they measure the behavior of this using these direct tension tests, and you can get a nice hardening type behavior with the material. I will note that fibers and Helix have been and can be used to make UHPC. The challenge for the industry is really making it more practical and lower cost, so that the application is not limited to just these little niche areas where you can afford to pay upwards of $1,000 per cubic yard for concrete. Does anybody know what that is? So as I was researching this, you know, and thinking about what level 5 would be. Level 5 is probably something that we've never seen. Level 4, UHPC would basically allow us to use concrete like it was steel in essence. We would have a hardening behavior like steel. But in a perfect world, looking into the future, we would have structures that are made of what are called isotropic materials, which means they behave the same in every direction: tension, compression, shear, uh, like truly like steel does. Um, and even going further, we would have structures that would fabricate themselves. So this is looking way down. So what this actually is this is an image for those of you who, I mean, they're very different. I mean, if you're a comic book junkie or, a kid of the 1980s or 70s, you might have seen this in a Superman comic or a book. This is called The Fortress of Solitude. And in the story, Superman is having some issues and not feeling in his place, and he basically walks to the North Pole. He has this crystal that he had found in his parents' basement or in his barn. Doesn't really know what it was. He throws the crystal into the ice, and all of a sudden, this fortress just grows out of the ground. Sounds pretty far fetched, but it actually has some. Um, it actually has some possibility in reality at some point. So to get to kind of a level 5 structure, which would be something that is isotropic and hardening and potentially even self-assembling, we need to kind of look almost at the nano scale. You can think about structures. I mentioned earlier that concrete's an amorphous material, which means that it's kind of a mixture. It's almost technically it's a solid that's comprised almost like it's a liquid. It's a mixture of different materials that don't have strong chemical bonds between them. Uh, what we What's more efficient is to have a crystalline or a polycrystalline structure. So steel is actually a polycrystalline structure, which is a random orientation of crystals, basically, crystals that are forming the iron, of iron and the alloys that are in a random orientation. Crystalline structures will generally have some symmetry to them, so they'll be anisotropic, which means they'll have different compression than tension. But if the crystals are arranged and bonded together in a random sense, they actually can have isotropic behavior. So, and also something that's crystalline or polycrystalline, because it's bonded together really at the chemical or atomic level, it's going to be much stronger. So some of the very interesting things that are going on in this field is that there actually is research that shows that you can take nano scale materials that are on typically a nanocrystal core, like what you see here, that is between 1 and 100 nanometers across, and you can actually put it into a condition under which it self-assembles structures that are on the millimeter scale. So obviously that's not the size of Superman's Fortress of Solitude on the North Pole, but it's a start. If you think about that, and the possibility of self-assembly, you can think about even ourselves. I mean, in essence, the cellular structure in our bodies have mechanisms in them that self-assemble our bodies. So with the advancements in biotechnology, advancements in material, it's not completely unfeasible to imagine a day where we could basically program a structure into a molecule or a cell or some type of self-replicating structure that would eventually create its own. It would eventually create an entire superstructure. The other place we can look for inspiration on this is biological. I mentioned cell structures, things like the cuttlebone, which is a undersea creature, has properties that are in some ways superior to concrete because these structures are really designed from at the molecular level up, as opposed to with concrete, we're mixing gravel, sand, and sort of the smallest material that might be in that engineered mix is maybe like a polysonic material like a fly ash. We're talking about materials that are being built from the ground up, not from pulverized materials down. Again, not feasible now, but in the future, certainly other possibilities. And then the last one, actually, my son had mentioned this to me because he had learned this in biology class or physics class, is one of the strongest materials actually in the world is the web of a black widow spider. It actually has a tensile strength to weight ratio that's like 10 times that of steel. So there have been a lot of scientists that have been trying to figure out, okay, why is that the case? And can it be replicated? And there's actually research where they've actually created structures that mimic the bond structure. The reason it's so strong is they're very strong hydrogen bonds in these materials. There have been scientists that have taken graphene and gotten it to form molecules that are that mimic that of the spider, and they're starting to kind of mix those materials with different polymers and things like that. So there's a lot of very highly adapted structures that are in nature that we might be able to leverage for construction at some point down the road. So my point is that really we're not going to see these structures really anytime soon, but definitely they're not completely out of the realm of possibility with advanced technology. So that's kind of my review of materials. I'm going to talk about a couple, and this is just going to take a couple minutes, talk about construction materials in a similar fashion, or construction methods. And we can kind of just go through this in a similar fashion. I mean, with the initial level just being hand finishing, screeding with a 2x4 and hand troweling and floating. We're already seeing a lot of development in terms of, and we've seen this for decades, but power equipment, laser screeds has really, I would say, made more than an incremental increase in the efficiency of construction, the quality of construction. But we can go beyond that. And there's a lot of stuff out there that's kind of like just starting to kind of sort of hit that potentially has additional advantages. So there are remotely operated screeds and trowel systems that are out there. The value is questionable because you still have to have an operator, but at some point those might be able to be completely autonomous, which reduces your labor and probably potentially could reduce error. However, given that concrete is such a tricky, there's so much that, so many variables involved, it's going to take a while to develop something that can be truly autonomous and finish as well as a very experienced concrete contractor can. So there's a screed that is automated. I don't think there's quite as much development. I couldn't find quite as much in terms of troweling. This is a autonomous troweling bot that is operated by a computer that is programming it to follow a certain pattern. Again, I think At this point, the value is limited because really you're just replacing somebody sitting on that trowel with somebody sitting in a computer who may not be able to do as well of a job as somebody sitting on it. But again, the sky's really the limit, especially as various AI technologies come out there. In order to really be able to do that, you would have to have some a machine that can basically learn how to judge, when to finish, how much to finish, what pattern needs to be followed to get a good finish, etc. Robotic manufacturing has obviously become very, very common in the Detroit automotive area. However, it's not as common for construction. There are certain applications of robotics that are used in construction, but because we're not in a controlled environment where everything's the same, it's not really an assembly line. It's a little difficult to implement, but doesn't mean that as robotic technology gets better, that it couldn't become more ubiquitous in construction. This is an example of the Mars canopy, which was a structure that used advanced materials. It was basically essentially a UHPC material that was formed with helix that was purchased by Jeff Bezos for the construction of a pavilion that looked. Let's see if I can get. There's the finished product that looked like this. So if you scan the QR code, you can see the video. It's pretty cool, and it's about the closest thing I've seen to using an advanced material to build a complex form like that without the need for rebar. The next, of course, and we've all heard a lot about this, is additive manufacturing or 3D printing. 3D printing is certainly interesting. However, it is a little bit weird because we're not really making a solid concrete structure. It's almost like you're more making a masonry structure that has voids in the center, and you still have to put quite a bit of reinforcement and framework in there. I'm going to be hosting at ACI a group that has a slip forming approach, a robotic slip forming approach that actually forms solid walls. In order to really enable this kind of thing, however, you need to have materials that don't really need to have reinforcement. Otherwise, you're adding reinforcement as you go. So 3D printing is a level 4. And then the last one, and this is something that's worth taking a look at, is self-assembly. And we talked about self-assembling materials, but there's actually a pretty cool website. If you go to this self-assembly lab at MIT, this QR code will take you there. It'll show you some of the stuff they're doing. One of them is this little chair that kind of you dump the parts into this water tank, and then it assembles itself into a chair like this. There's also some more structures that are a little bit more civil. This is a stone structure that actually uses a form of a self-assembling method to put it together. So I'll leave that to you to look at. So I really, we're kind of running out of time here. I really enjoyed having the opportunity to talk to you about this kind of off-the-wall topic today. The reason that we would think about these things and recognizing some of the stuff that's going on at MIT and, Superman's Fortress of Solitude are way outside of the ballpark of where we're going. Even progressing down the scale a level or two, or being willing to use an alternate method that might not be in the code, but is allowed in evaluation reports, does allow you access to innovate and provide better solutions to your customer. These are some of the benefits to each group that you might encounter. And at Helix, really, we pride ourselves on really taking those steps, and we really have. I mean, and I'm very proud that we have taken those steps. Now Helix is not, all the way down the scale, but we've been able to do some things in the market in ordinary applications like residential walls, large foundation slabs, slabs on ground, uh, large footings that have not been able to be accomplished by others because of the properties of the material, but also are willing to work with our customers to innovate. We work with customers very closely. We have a group of engineers that are available and at your disposal to work through projects and really find that value and ultimately benefit for the end user that will keep them coming back to you time and time again. And if you are an end user, that's going to give you a more resilient structure, a more sustainable perhaps structure, and lower maintenance type structure. So we do many other presentations that are more Helix specific. If you have questions about Helix, I definitely encourage you to reach out to us. You can go to our website to this spec tool. It has all kinds of information about where you can use Helix. If you have more general questions that you did not ask today, you can just go to the Contact Us page on our website. And we're definitely happy to discuss with you what your applications are and where you might be able to benefit from the product. So with that, this is my contact information. If you would like to connect with me, you can scan that QR code and it will take you to my LinkedIn profile. If you would like a copy of any of the papers I referenced in this presentation, I'm happy to send them to you. Or if you'd like more information about Helix, you can go onto that website, contact us form, or reach out to me. And then you can also follow us on our various social media platforms. So anyways, I really appreciate everybody's time and attention. We went a couple minutes over here. I'm glad I did not decide to include the remaining 12 slides on design. But if you have questions, please feel free to throw them in the chat. I'll stay on for a couple 5 minutes and answer some of the questions that are in here. But otherwise, have a great weekend. Hope the weather is holding where you are, and that you have a good weekend. Thank you very much. So yes, we can definitely send, if you send us drawings to the Contact Us page or the Submitted Drawings, or just email us, we definitely can get that information to you. Typically, it's a couple of days. Our engineering team will review it, get you kind of some preliminary designs with Helix, and then you are able to make a decision as to whether you want to move forward. Once that decision's made, we will provide more detailed submittals to satisfy your engineering team. So thank you. Yep, we'll look for that. Let's see. Are there resources for designing continuous trench footings from Tyler? Yes, there are. If you go to that spec tool, which I can put that back up, remove this. The spec tool has a flyer in there that has actually designs or design tables for use with strip footings. You can also reach out to Peter and he can get you applications that are more specific. If your strip footing is just residential and it falls within certain limitations within IRC, it may be possible to just use a standard 9 pound per cubic yard dosage. So we can certainly help you assess that. If you go to spec tool and footings, there's some information in there. Or if it is residential, you can look at our ICC-ES report, which you can also find in the spec tool. So we do a lot of ICF construction. Actually, our whole team was out on a Helix ICF construction Habitat for Humanity build yesterday, where we designed basically a triplex with Helix reinforced walls, and our whole team got to participate in that. We have extensive experience in both above and below grade ICF. Again, there's a flyer that specifically addresses ICF in the spec tool. Also, there's a resource called EER 3949 from ICC that has standard details and specifications for ICF using Helix based on how tall your structure is, what type of soil, what type of wind exposure, etc. Hanny had a question about lightweight concrete. The lightweight concrete, we address that under our IAPMO approach. We would have to, if you wanted to get Peter the details of what type of lightweight concrete you're using, we're able to provide designs. A lot of times where we see lightweight concrete is in slab on metal deck applications. Testing of Helix and torsional elements. There has been some testing of Helix in larger scale elements in the laboratory. Most of it's focused on bending. Torsion is not something that we typically consider in the designs that are common for Helix, which would include your wall sections, your footing sections, and your soil supported slab sections. So we don't typically see that a lot. We assess the behavior of Helix with a variety of coarse aggregates. Most of the time, coarse aggregates are ranging from 3/8 up to about 1.5 inches. Yeah, I mean, to Peter's point, really, Helix doesn't require special finishing practices. You're just going to follow your normal finishing and placing practices that you normally would with concrete. So this is great. We've had a lot of questions. Hopefully you've enjoyed this. Maybe some of you will be inspired to go rent the 1978 version, the original Superman movie this weekend. If you do, good luck with that. I'm sure the graphics and special effects probably aren't quite up to what we're used to today, but you might see an example of a self-assembling structure. So anyways, that being said, thank you, everyone. You will get an email follow-up with a copy of the presentation. If anybody wants any of the articles, please don't hesitate to reach out to us. Thanks, everyone.